Another thing that you can do with truth tables is to determine relationships between two or more different kinds of statements. One of the relationships that you can have between statements is that of logical equivalence, okay? So when two truth functional statements have identical truth values, they are referred to as being logically equivalent, okay? So let's compare these two statements. We have the statement here. It is not the case that both S and H, okay? And S stands for Superman is a great movie, okay? And H stands for Harry Potter is a great book. So this statement actually states it is not the case that both Superman is a great movie and Harry Potter is a great book, okay? So we're going to compare this statement now with this statement here, okay? And this statement says, it is not the case that Superman is a great movie, or it's not the case that Harry Potter is a great book, okay? So we're going to compare these two statements. Notice that they are structurally different, okay? This is a negation with a conjunction inside the parentheses. So this is a negation that is negating a conjunction. And this is a disjunction with negations as its main components, okay? So they are structurally different statements. Okay? Now, in order to do a truth table for two or more statements, what you want to do is simply do the same process as you would for doing a single statement, except you put the statements right next to each other, okay? And you separate the statements with a slash, okay? So you know where one statement ends and the other one begins, okay? And then you make the lines according to the same rule, okay, that you would use for one statement. So the rule again is L equals 2 to the n power, okay? So the number of lines equals 2 to the n power, where n equals the number of distinct variables, okay? So notice here we only have two distinct variables among the statements, okay? So there's an S and there's an H, and this one only has an S and an H as well. So we only have two different distinct variables among the statements, okay? So the number of lines will be 2 to the second power, okay? And that's 2 times 2, okay? Which gives you 4, okay? So we have 4 lines here, okay? Now, after we have determined how many lines and we went ahead and set up the columns and the cells, we need to first distribute the truth values for the distinct variables, okay? Same method applies regardless of whether or not you have one statement or two statements or however many statements you're comparing, okay? You take, again, the number of lines that you have and you cut that number in half, okay? This time, it's going to be 2, okay? Then, you give the first distinct variable, okay, the truth value, so that's going to be this S, the truth values, true, true, and false, false. So all true for the first half and all false for the second half, okay? So this is what you'll have. Then for the next distinct variable, you're going to cut the halves in halves. So now you have quarters, okay? And you're going to alternate the quarters starting with true, true, false, okay? So this is going to be for our H, and this is what we'll have, true, false, true, false. Now remember, we only have two distinct variables, so H was our last distinct variable. So we know that we've done our initial distribution of truth values correctly because for the last distinct variable we have, we're alternating in every row, true, false, okay? Now over here for this statement, we've already given truth values to this S over here by giving truth values for the S over here. So we're simply going to use the truth values in this column again for the truth values here for this S, okay? And then, same thing, for the H over here, we've already given truth values for the H over here. So because the H occurs here as well, we're going to go ahead and use the same truth values that we've given the H over here to the H over here, okay? So this is what we'll have. Now what we want to do is determine the truth values for the logical operators, okay? Now remember, for the logical operators, you want to start out with the smallest components inside the parentheses if there are parentheses and working your way out. So let's start with this statement over here, okay? So this statement over here is a negation, and we know that because the smaller component is whatever is in this parentheses, and the negation is outside of the parentheses, and it is negating everything that is inside the parentheses, okay? So we're going to start again with the smaller components and work our way out, okay? So that means we're going to start with what's inside the parentheses and then work our way outside to the negation, which is the main operator. So we're going to save that for last. Now inside the parentheses we have a conjunction. We have a conjunction of S and H. So in order to determine the truth value for the conjunction, which is this conjunctive dot here, we're going to use the truth values for its component parts, okay? So the conjunction, the parts that make it up, is the S and the H, okay? So we're going to use the truth values for these two columns, the S and the H, along with the truth function of the logical operator that is a dot, okay, in order to determine the truth value for the entire conjunction, okay, which we will put underneath the dot operator, okay? So remember the truth function rule for the conjunction dot is that the conjunction is only true when both parts that make it up are true. In all other cases, it's false, okay? So here, you'll have the following truth values, okay? Where S is true and H is true, the conjunction is true. Where S is true and H is false, the conjunction is false. Where S is false and H is true, the conjunction is false. And where S is false and H is false, the conjunction is false, okay? Now that we've determined the truth value for the component part that makes up the negation, we're going to do the truth value for the negation, which will go underneath this logical operator of the tilde, okay? Now this negation negates everything that's inside the parentheses, okay? And everything that's inside the parentheses is a conjunction, okay? So we will be using the truth values for the conjunction, because that's what's inside the parentheses, in order to determine the truth values for the tilde, okay? So the tilde truth function is when a statement has a certain truth value, let's say the conjunction has a certain truth value true, then the negation of that will be false, okay, will be the opposite. So given that, and using these truth values here for the conjunction to determine the truth values for the tilde, we will have the following truth values for the tilde, okay? So when the conjunction is true, the negation will be false. When the conjunction is false, the negation will be true. When it's false, it's true. When it's false, it's true, okay? Now we're done with this statement for the truth table, but we have to finish that statement. So let's move over here now. Okay. So here we have the disjunction of two negations, okay? So the main operator for this statement here is the disjunction. And the two largest components that this disjunction brings together is the negation S and the negation H, okay? So we're going to leave this column here under the wedge last, okay? And we're going to do the truth values for the component parts before we do this one here, the truth values for the wedge, okay? Let's start with this one over here. Okay, so here we have another negation, okay? So in order to determine the truth value for the negation, which will go under the tilde, we use the truth values for the statement it's negating, which is the S, okay? Along with the truth function of the tilde operator, okay? So when we do that, we will have the following truth values. When S is true, the negation of S will be the opposite truth value, false, okay? S is true, the negation of S will be false, and when S is false, the negation of S will have the opposite truth value, so it will be true, okay? So when S is false, again, tilde S will be true, okay? So now we're done with this side of the disjunction, we'll move on to the other side of the disjunction. Here, again, we'll use the truth values for the statement that the negation is negating in order to determine the truth values for the negation, okay? So here we're going to use the truth values for the H, okay? And we're going to use the same rule for the tilde operator in order to determine the truth values here for that tilde. And we'll end up with this, okay? So the rule is, if H is true, then tilde H has that opposite truth value, so it'll be false, okay? And when H is false, tilde H will have the opposite truth value, which is true, okay? And so on. Okay, now that we've done the truth values for the component parts, we can move on finally to the truth value for the main operator for this statement, okay? And This statement here, remember, is composed of the negation S, okay, and the negation H. So we're going to use the truth values for the negation of the two statements in order to determine the truth value for the wedge, okay? So here you have false, and here you have false, okay? So the truth value for the wedge then, using the truth function for the wedge operator, will be false, okay? Because remember, the rule for the truth function of the wedge operator is the only time a disjunction is false is when both parts are false, okay? In all other cases, it's true. So we'll have false here, and using the truth values for the other columns, these are the truth values that we'll get, okay? So when you have false here, and you have true here, you'll have true. Okay, the disjunction will be true. And if you have true here and you have false here, then the disjunction will be true. And if you have true here and you have true here, the disjunction will be true. Okay? So now that we've done the truth table for both the statements, and notice how there's one truth table and we put both statements on one truth table, we can compare the logical properties of both statements, okay? So here, looking at this statement first, remember that the truth values for this entire statement occur under the main operator, okay? So these are all the possible truth values that this statement, which is a negation, can have. Now notice, looking at this statement by itself, okay, it is a contingent statement. Why is it a contingent statement? So this is a contingent statement. Okay, why is it a contingent statement? Well, you can see that this statement, according to the truth table, can be false sometimes and other times true, depending on the truth values of its component parts. Okay, so it's not going to be always false or always true. In this sense, it's contingent. Okay, so the easiest way to determine a contingent statement is when you look at the truth value for it and you see that there are both true and false truth values that occur in the column for its main operator. If that's the case, then this statement is contingent. It could possibly be true or false. Okay, remember, these are all possibilities of truth values that this statement can have. Okay, also when you look at this statement here, and this is basically the column that represents the truth values for this statement here, okay, all the possible truths that this statement can have. Notice that this statement as well is a contingent statement. Okay, it's contingent because if you look at the column for its main operators, you have both true statements and false statements. So this statement can possibly be false as well as true. So it is a contingent statement. Okay, now those are properties of the individual statements themselves. We can also look and compare the statements together. And when we do that, what you should notice is that in every row, okay, where this statement has a certain truth value, this statement has the exact same truth value, okay? So where this is false, this is also false. Where this is true, this is also true, okay? Okay? This means that these two statements are logically equivalent. Okay, so they're logically equivalent because the two statements have the exact same truth values in every row of the truth table. Okay, so whenever this is false, this statement will also be false, and whenever this is true, this statement will also be true. Okay, so these are called logically equivalent statements. Logical equivalence is a relationship between statements. Okay. It's not a property that belongs solely to one statement alone. Like contingent is a property that belongs to one statement by itself. So this statement is contingent and this statement is contingent, okay? However, these two statements have the relation of logical equivalence, okay? So logical equivalence is a relation between two or more statements, okay? Okay, moving on. Another relationship is that of contradictory, okay? So let's compare these two statements here. So you have this statement here, tilde F wedge S, okay? And then the other statement is F dot tilde S, okay? F stands for Jennifer loves football, and S stands for Jennifer loves soccer. So this statement here is saying it's not the case that Jennifer loves football or Jennifer loves soccer, okay? And this statement here after the slash is saying Jennifer loves football, and it's not the case that Jennifer loves soccer, okay? So we have two different statements, and they're structurally different, okay? This statement here, the main operator for this statement is the wedge, so this is a disjunction, and the main operator for this statement here is the dot, so that's a conjunction. Okay, so doing the truth table for these two statements now so that we can compare the statements. We can also look at the properties of each statement individually. Okay, we go ahead and set up the number of lines and set up the columns. Okay, I'm not going to go over that again just because it's the same procedure. Okay, so now that we've set up the lines and the numbers of columns, we're going to distribute the truth values for the distinct variables. Notice out here we only have two distinct variables among the statements, okay? So we have an F and an S, and those are the only two distinct variables we have among the statements because this statement also has an F and an S, okay? So we have two distinct variables. So coming here to the first distinct variable that we get to when we go from left to right, okay, we're going to cut the number of lines that we have in half again, okay, so in 2. Okay, so we have 2 by 2, okay? And for the first half, we're going to do all true, and the second half, we're going to do all false. And this is what we get. Then, for the next distinct variable, we cut the halves in halves, okay? So now we have quarters, and we alternate every quarter, starting with true, and then false, and then true, false, okay? So this is what we'll have, okay? Now, this is the last distinct variable that we've come to, and we know that we've done the initial distribution of truth values correctly because we're alternating in every row, true, false, okay? So for these truth values over here, for the F over here and the S over here, because we've already given those variables truth values here and here, we're simply going to use these truth values again here and here, okay? So we have this, true, true, false, false, and this, true, false, okay? So now that we've done the initial distribution of truth values for the distinct variables and the other variables, okay, we want to determine the truth values for the logical operators. We have two statements here, right? So it doesn't matter which one we work with first, but we want to do both statements, okay? And we're going to go ahead and do this statement first, okay? So here, we have a disjunction that's the main operator, so this is a disjunction, and this disjunction pulls together the not F, that's one of the main components of the disjunction, and the S, okay? Now we already have truth values for S, so now we need truth values for the not F, okay? And in order to determine the truth value for any negation, okay, you take the truth values for the statement it's negating and use the truth function for the tilde operator. Okay? And remember the rule for the truth function of the tilde is whenever you have a statement that has a certain truth value, so a statement F, for example, then the negation of that statement will have the opposite truth value. Okay? So using that rule and this column here for the truth values, we will have the following truth values. Okay? So when F is true, negation F will be false. F is true, negation F will be false. F is false, negation F will be true. F is false, negation F will be true. Okay? Now, because we've done the truth values for both the component parts, we can do the truth values for the main operator, which is the wedge. Okay? So we want to use, again, the truth values for the component parts in order to determine the truth value for the main operator, okay, as well as the truth function for the operator. In this case, it would be the wedge. So we would use the truth values for the negation because the negation is the main part of this disjunction on this side, and the truth value for the S, which is the main part of this disjunction on this side, okay? So using these truth values here and the rule for the logical operator that is the wedge, we will have the following truth values, okay? So when the negation is false and S is true, the disjunction will be true. When the negation is false and S is false, the disjunction will be false. When the negation is true and S is true, the disjunction will be true. And when the negation is true and S is false, the disjunction will be true. Okay? Remember, the only time that a disjunction is false is if both its component parts are false. So here, you have the only time that this disjunction is false when both its components are false. Okay? And all other times you have true because its components are not both false. Okay? Okay. So now we've done this statement here, we must move on to this statement over here. Okay? So for this statement over here, it's a conjunction, that's the main operator, and the largest components that this conjunction brings together is the F and the not S, okay? So we want to first do the truth values for the component parts before we do the truth value for the main operator. We've already had the truth values for the F, so now we have to do the truth values for the negation S. Same rule applies here, right? Because we have a negation operator, okay? So when you have any statement S, okay, then not S will be the opposite truth value that that statement S has, okay? So using that rule, we'll have the following truth values, okay? So when S is true, you'll have the opposite truth value for the negation of it, and when S is false, you have the opposite truth value for the negation of it, and so on, okay? Okay, now that we've done the truth values for the component parts, okay, we're going to use the truth values for the component parts in order to determine the truth values for the main operator, which is the disjunctive dot, okay? The truth value for the component parts was the F, okay, and the negation S, okay? And the truth values for the negation S is actually under the negation. So we're going to use the truth values for the F down here and the negation here in order to determine the truth values for the conjunction, okay? And along with the truth function for the logical operator, the dot. The rule for the logical operator dot, the one rule, is that the conjunction is true only when both its parts are true. So when both its parts are not true, okay, it's going to be false, okay? So using that rule and these two columns here, the F column and the negation column, we will have the following truth values, okay? So when F is true and the negation S is false, the conjunction will be false. And when F is true, the negation S being true, the conjunction will be true. When F is false and the negation S is false, the conjunction will be false. And when F is false and the negation S is true, the conjunction will be false. Okay? Okay, so now we've done the truth values for both statements, okay, for the truth table. Now that we've done that, we can compare the statements as well as determine the properties of each individual statement by itself. If we look at this statement here, notice that the truth values for this statement, which occurs under the main operator, which is the conjunction dot, is that this statement can be false as well as true. So this statement is a contingent statement as well. Okay? And then if you look over here to this statement here, the truth values being under its main operator, okay, we see that for this statement as well, you can have both true and false statements, okay? So it's possible for this statement to be true as well as false, okay? So this statement too is contingent, okay? Now we can also compare the statements, okay? Notice how when we compare these two statements, okay, we see that whenever this statement is true, the other statement has the opposite truth value, okay? So this is true, this is false, this is true, this is false, okay? And whenever this statement is false, this statement here has the opposite truth value, true, okay? So this statement will always have the opposite truth value compared to this statement. And this statement will always have the opposite truth value compared to this statement. Because these two statements then will always have the opposite truth value, these two statements are contradictory statements, okay? Contradictory statements are the opposite of logically equivalent statements. So remember, logically equivalent statements are two statements that have the same exact truth values. These two statements have the opposite truth values. So these two statements are contradictory statements. Also, once again, remember, contingency, okay, that a statement is contingent is a property of an individual statement, okay? So this statement is contingent and this statement is contingent. However, contradictory is a relationship between statements, just like logical equivalence, okay? So two statements or more can be contradictory, but a single statement is contingent. Also, contradictory means something different than self-contradictory. So self-contradictory is a property of a single statement, okay? That statement being necessarily false, okay? Whereas contradictory is a relationship between statements, and that relationship is that when one statement has a certain truth value, the other statement will have the opposite truth value, okay? And moving on, we have the relationship of consistency, okay? So when two or more statements that have at least one line on their respective truth tables where the main operators are true, the statements are consistent, okay? So what does this mean? Well, let's do a truth table for these two statements, okay? So here we have the statement R wedge B, okay? And here we have the statement R wedge not B, okay? So R stands for Bob received roses for his birthday, and B stands for Bob received a baseball for his birthday, okay? So this statement reads, Bob received roses for his birthday, or Bob received a baseball for his birthday, okay? And this statement here, which is separated by a slash, reads, Bob received roses for his birthday, or Bob did not receive a baseball for his birthday, okay? Okay, so just like all other truth tables, okay, regardless of how many statements you're doing a truth table for, okay, you set it up exactly the way that we've discussed in the past, okay? You put the statements here. For the statements, when you're comparing statements, you want to put a slash in between the statements so you know where one statement ends and the other one begins, okay? You figure out how many lines that you need, and in order to figure that out, you use the rule L equals 2 to the n, so the number of line equals 2 to the n, where n equals the number of distinct variables. So here we have two distinct variables among the statements. So this has R and B, and this one uses R and B again, okay? So we only have two distinct variables. So 2 to the second power is 4, so we have 4 lines here, okay? So we went ahead and put the columns and the lines in. Now to initially distribute the truth values for the distinct variables, okay, we again cut the number of lines we have in half and give the first half all true and the second half all false. So here's the first distinct variable that we'll come to. So we cut the number of line in half, give the first half all true and the second half all false. So that's what we'll have. Then for the second distinct variable we come to, reading from left to right, okay, we cut the halves in half, so this time we have quarters, and we'll alternate true, false, between the quarters, okay? So B will get true, false, and because we have two distinct variables, B is our last distinct variable, and we know that we have distributed initially the truth values correctly, because for our last distinct variable, we're alternating true, false. So here we have R occurring again, so we simply use the truth values that we gave R the first time over here. So this is what we'll have. And for B occurring here again, we use the truth values that we gave B initially, so this is what we'll have. Okay, now what we want to do is determine the truth values for the logical operators, okay? Because we have two statements, we're going to work with one statement at a time. Okay, so here on this side, okay, this statement here, notice that we have a disjunction, which is the main operator, okay, that wedge, which means this disjunction pulls together the two components, that is the R and the B. So in order to figure out the truth values that goes under this disjunctive wedge, okay, which are the truth values for this whole statement here, we're going to use the truth values for R, the truth values for B, and the truth function for the logical operator, which is the wedge. Remember, the one rule for the logical operator, that's the wedge, is that a disjunction is only false when both its parts are false. In all other cases, it's true. Okay? So using that rule and these two columns here, we will have the following truth values. Okay? So when R is true and B is true, the disjunction will be true. When R is true and B is false, the disjunction will be true. When R is false, the B is true, the disjunction will be true. And when R is false and B is false, the disjunction will be false. Okay? This column here then gives us the possible truth values that the disjunction, okay, which is this entire statement here, okay, this disjunction can have, okay? Now that we're done with this statement here, we're going to move over here and do this statement, okay? This statement is a disjunction as well. The logical operator for this statement, that is the main operator, is the disjunction, okay? This disjunction pulls together the two main components, which are the R and the not B, okay? So we want to do the truth values for the main components before we do the truth value for the main operator. We already have truth values for R, so now we want to do the truth values for not B. Again, we use the truth values for B here because the negation is negating the statement B along with the truth function for the logical operator, that's the tilde, in order to determine the truth values for not B, okay? So remember, the truth function for the tilde is when a statement has a certain truth value, tilde that statement, the negation of that statement, will have the opposite truth value, okay? So using that rule, we will have the following truth values, okay? So where B is true, tilde B is false, tilde B is true, tilde B is false, tilde B is true, okay? Okay, so now that we've done the truth values for the component parts, okay, we are going to do the truth value for the disjunction wedge, okay? This is the main operator for this entire statement, okay? And again, we're going to use the truth values for the component parts that this disjunction wedge pulls together in order to make the complete statement. So that would be the truth values for this R, which is one part of that disjunction, and the truth values for not B, okay, which is the second largest part of this disjunction. And not B, the truth value for that statement, is underneath the tilde. Okay? So the logical operator now that we will be using is the wedge. Okay? So the truth function for the wedge is the only time a disjunction is false is when both of its parts are false. In all other cases, it's true. Okay? So using that, we will have the following truth values. Okay? So when R is true and not B is false, the disjunction will be true. When R is true and not B is true, the disjunction will be true. R is false and not B is false, the disjunction will be false. And R is false and not B is true, the disjunction will be true. Okay? So this column here gives you the truth values that are possible for this statement here. Okay? So these are the possible truth values that this statement can have. Okay? Depending on the truth values of its component parts. Okay. So now that we have determined the truth values for each of these statements, okay, we can look and see that both of these statements are contingent statements, okay? So this one, it's possible for it to be true as well as false. So this one is contingent as well, okay? And this one is possible for it to be true as well as false, okay? So this one is also contingent. And remember, contingent is a property of each individual statement, okay? We can also compare these statements and see, is it the case that these are logically equivalent statements? Well, although it's the case that they have the same truth values here, notice that they have different truth values here. So where this is true, this is false, and this is false, this is true. This means that these are not logically equivalent statements, because for logically equivalent statements, you have to have the same truth values, okay, on every line between the statements. They're also not contradictory statements, okay? Why? Because although they have opposite truth values here, they have the same truth values here. And for contradictory statements, you need to have the opposite truth values on every line in between statements, okay? However, these two statements are consistent statements, okay? Meaning that there's at least one line. You can have more than one line, but there's at least one line where the statements can be true at the same time. So notice here, where this statement is true on this line, this statement is also true on this line. And also here, where this statement is true on this line, this statement is also true on this line. Now, they have the opposite truth values here, but that's not what we're concerned with when we're concerned with consistency. When we're concerned with consistency, we want to know, is there at least one line, okay, in which the statements can both be true? Okay? And here, there are actually two lines where the statements can both be true. Okay? What this tells us is that there's a possible case, okay, where these two statements can both be true at the same time. However, it does not imply that it is definitely the case that these two statements are both true at the same time. Okay? Why? Because there's also a possible case where they can have different truth values, okay, at the same time. Remember, each of these lines represents a possible truth value that these statements can have. Now, one of these lines would be the actual truth values, okay? However, as of yet, we don't really know which one is the actual truth value because we don't know what the truth values for these individual statements are. However, consider this. R stands for Bob received roses for his birthday, okay? And let's say that it is actually true, okay, that Bob received roses for his birthday, okay? And B stands for Bob received a baseball for his birthday. And let's say that it's actually false, that Bob received a baseball for his birthday. Okay? Then if you see here, where you have on the truth table, where R is true, okay? So here you have R being true, and you have R being true here, but also where you have B being false, which is only here, where you have R being true and B being false, okay? Okay, and notice for this statement as well, R being true and B being false, okay? In this scenario, which is the actual case, okay, because we said it's actually the case that Bob received roses for his birthday, and it's actually the case that Bob did not receive baseball for his birthday. In this case, you have this disjunction being true and this disjunction being true as well, okay? So this line here, okay, gives us the truth values, that's the truth values for the actual world, okay? Because in the actual world, it is true that Bob received roses for his birthday, and in the actual world, it is false that Bob received baseball for his birthday, okay? So this row here gives you the truth values for the actual world, okay? These statements in the actual world. However, if the world was different, okay, then we could have other truth values, okay? So although this is the line that represents the truth values for the actual world, it's still the case that each line represents a possible case in which these statements can be true or false, okay? So each line represents a possible truth value that these statements can have depending on their form or structure, okay? Okay, so now let's look at another relationship between statements. When two or more statements do not have even one line on the truth table where the main operators are both true, the statements are inconsistent, okay? So let's look at this statement here. Here we have one statement, C horseshoe M, and then we have that differentiated by a slash here from this other statement, C dot tilde C, okay? And C stands for Caroline is a psychology major, and M stands for Michael is a psychology major, okay? So this statement here reads, If Caroline is a psychology major, then Michael is a psychology major. And this statement here reads, Caroline is a psychology major, and it's not the case that Caroline is a psychology major, okay? So we have two different statements. So we're going to do truth table again for these two statements so we can compare these statements, okay? And I'm not going to repeat the procedures again, okay? However, just note that first we start with this distinct variable, okay? I already did the setup for how many lines and so on we're going to have, okay? So this distinct variable, you'll have the following truth values, true, true, false, false. And for this distinct variable, you'll have the following truth values, true, false, true, false. Then for C here and C here, you'll have the same truth values as you did here. Okay, and now we want to determine the truth values for the logical operators. Okay, so we have two statements. We're going to work with one statement at a time, and we'll do this one first. Now this is a conditional statement. Okay, so this is the main operator for this statement. And because this is the main operator for the statement, we're going to use the truth function for the horseshoe. Okay. The one rule for the truth function of the horseshoe is that a conditional statement is false only when the antecedent is true and the consequent is false. In all other cases, the conditional statement is true. Okay? So using that rule, we will have the following truth values. Okay? So this statement is true when the antecedent is true and the consequent is true. It's false when the antecedent is true and the consequent is false. It's true when the antecedent is false and the consequent is true. And it's true when the antecedent is false and the consequent is false. Okay? Then moving on to this statement here. This statement is a conjunction. Okay, that's the main operator. And it's pulling together the C, which is one of its main components, and the not C. Okay? So we're going to do the truth values for the not C first, and then the truth value for the conjunction. Okay? So again, using this row here, the statement that the tilde is negating, as well as the truth function for the tilde, we will get the following truth values. Okay? So wherever this C has a certain truth value, the tilde will have the opposite truth value. Okay? Now, after we have determined the truth values for the component parts, we're going to determine the truth value for the main operator. And we're going to use the truth values for the component parts to determine the truth value for the main operator. This case is the conjunctive dot. Okay? So we'll use the C, which is one part of that conjunction, and the negation C, which composes the second largest part of that conjunction. Okay? And the truth function for the dot. The truth function for the dot is that the conjunction is true only when both conjuncts are true. Only when both of the parts of the conjunction are true. In all other cases, it's false. So using that rule, we will have the following truth values. Okay? Notice that when C is true and negation C is false, the conjunction will be false. When C is true and negation C is true, the conjunction will be true. When C is false and negation C is false, the conjunction will be false. And when C is false and negation C is true, the conjunction will be false. Okay? So now that we've done the truth table for both the statements, okay, we can compare the statements. We can also determine properties of each individual statement. So this column here determines the possible truth values for this statement, and this column here determines the possible truth values for this statement. Okay? So when we look at the truth values here, the possible truth values here for this statement, we notice that this statement can possibly be false as well as true. So this is a contingent statement. Okay? And if you look at this statement over here, it's also the case that this statement can be true as well as false. So this is also a contingent statement. Okay? Now we can consider the relationship between these statements. Okay? Are these statements logically equivalent? The answer is no. Okay? It's not the case that where one has a certain truth value, the other one has the same exact truth value. Okay? So they have different truth values here, and here, and here, and here. Now we want to ask, is it the case that they are contradictory statements? Well, if you look here, it is the case that where one has a certain truth value, the other one has the opposite truth value. Okay? So here it's true, here it's false, here is false, here is true, here is true, here is false, and here is true, and here is false, okay? So these two statements are in fact contradictory statements, okay? So they are contradictory statements. However, not only are they contradictory statements, these statements are also inconsistent statements, okay? How do we know that they're inconsistent statements? Well, there's no line where these two statements are true at the same time, okay? So notice how where this is true, this is false, and where this is false, this is true. True, false, true, false. So there's not a single line, not even one line, where both of these statements are true at the same time. And because of that, not only are they contradictory statements, they are also inconsistent statements, okay? It's always going to be the case that contradictory statements will be inconsistent statements. However, it is not the case that inconsistent statements are always contradictory statements. So now that we know how to do truth tables for statements, individual statements as well as multiple statements, we can go ahead and understand how to do truth tables for arguments.